Let's talk about something we use every single second, but almost never actually think about: numbers. We're going to dive into the hidden logic behind them, the very logic that runs everything from your own brain to the device you're watching this on right now. Okay, let's kick things off with a really simple question. You look at this and your brain immediately says 10. We all know it, but have you ever, for just a second, stopped to ask why? Why does a 1 next to a 0 mean this specific amount? It feels totally natural, but the answer to that question is the key to unlocking everything else. So where did this whole idea of 10 even come from? Well, the answer has been right in front of us, or, right at our fingertips this whole time. Turns out our entire way of thinking about numbers was literally shaped by our own two hands. This system that we use without even thinking has a proper name. It's called base 10, or you might hear it called the decimal system. It's the default setting for human counting, and it feels so right to us for one very, very simple reason. And the reason is, well, it's kind of beautiful in its simplicity. We have 10 fingers. Early humans used their fingers to keep track of things, and that simple fact of our anatomy shaped how our brains work and how our civilizations were built. We created a system with 10 unique symbols, 0 through 9, because that's just what we had to work with. But hang on, if we only have 10 symbols, how do we count past 9? This is where the real genius of our number system comes into play. It's a concept called place value, and it all comes down to a simple idea. A number's worth isn't just about what it is, but where it is. So let's take a number we all recognize, 345. The symbols themselves are pretty basic, a 3, a 4, and a 5. But all of their meaning, all of their power, comes from their position, right? You don't read this as separate digits, 3, 4, 5. Your brain instantly knows that the position of each of those numbers gives it a totally different weight. That 3 isn't just a 3, it's way more powerful than the 5, and it's all because of where it's sitting. Let's really break that down. The 5 is in the ones place, so it's just worth 5. The 4 is in the tens place, so it's worth 40. And the 3, it's all the way over in the hundreds place, which makes it worth 300. Every time you move one spot to the left, the value gets multiplied by 10. That's it. That's the fundamental rule of our entire base 10 world. Now, this whole base 10 system, it works perfectly for us 10-fingered humans. But our machines, well, they don't have fingers. At their very core, they deal with a much, much simpler physical reality. And that reality forced them to find a completely different way to count. Okay, so here's the huge difference. We have 10 fingers, so we invented 10 digits. A computer, deep down, is just a massive collection of tiny little electrical switches. And a switch can't be a 7 or a 4. It can only be one of two things. It's either on or it's off. That is the only language it truly gets. To solve this two-state problem, the pioneers of computing created a brilliant new system. It's called binary, or base 2, and it's a number system that uses only two digits, 0, which means off, and 1, which means on. This right here is the native language of every single computer on the planet. So how in the world do you represent all the amazing complexity of our world with just two little numbers? Well, you do it the exact same way we do in base 10, with place value. So come on, let's learn to speak a little computer language. So check this out. The principle is exactly the same as our system, but the magic number changes. Instead of each place value being 10 times bigger than the one before it, in base 2, it's only 2 times bigger. So the columns aren't ones, tens, hundreds, they're ones, twos, fours, eights, 16s, and so on. Each one is just a power of 2. Let's actually try counting. It's pretty cool. The number 1 is easy. It's just 1. But now, to show the number 2, we've run out of digits. So, just like we do when we go from 9 to 10, we add a new column and start over. So 10 in binary doesn't mean 10. It means you have 1, 2, and 0 ones, which, hey, adds up to 2. Want to make 3? Easy. You just need 1, 2, and 1, 1. So you write 1, 1. How about 5? Well, you need 1, 4, no 2s, and 1, 1. So you write 1, 0, 1. It's the same logic, just a different base. I know, this might feel a bit abstract, maybe a little nerdy, but this incredibly simple on-off language is the absolute bedrock of our entire digital world. Let's connect this string of ones and zeros back to the screen you're looking at right now. Just let that sink in for a second. Every single thing. The video you're watching, the different colors on the screen, even the sound of my voice hitting your ears, it has all been translated into a mind-bogglingly long string of ones and zeros that your device is decoding at incredible speed. And just to give you a sense of the scale here, a single high-quality picture that you take on your phone is made up of roughly 24 million of these ones and zeros. That's 24 million tiny little switches, all flipped on or off in a perfect pattern just to create one image. It's absolutely staggering. So really, when you boil it all down, our entire digital experience, from the most complex video game to a simple text message, it's all built on this incredibly simple foundation of two states. We just get to see the amazing, finished product. So that leaves us with this final thought. We humans built our world on 10 digits because of our hands. Computers built their digital world on 2 states, on and off. But as we move into wild new frontiers like quantum computing, where things can be both on and off at the same time, what's the next base number that's going to define our future? What comes after 10 and 2?